So let's take a look at negative transcriptional control. And we're going to be looking at negative transcriptional control of an inducible operon. And then we'll look at negative transcriptional control of a repressible operon. And then we're going to be working with a repressor protein, because remember, with negative transcriptional control, what we're using to turn the operon on and off is a repressor protein. And the repressor protein, where it binds to the DNA and the operon, is called the operator. And when the repressor protein is bound to the operator, then RNA polymerase is not able to bind to the promoter, and that is going to inhibit transcription, and that will turn the operon off. All right, so let's go ahead and we'll draw this out. All right, so with negative transcriptional control, we're going to be using our repressor protein to turn our operon on and off. And I'm going to be putting one of these 4 scenarios that we draw on the exam. So the first question I'll ask you is just to define what an inducible operon is. So what I'm looking for in the definition of inducible operon is just it's turned off unless the substrate's present. So that's all you have to write for the definition of inducible operon. So turned off unless the substrate's present. All right, so the second part of the question will be, well, how would it be turned off when it's under negative transcriptional control? So let's draw it turned off for part B of the question. So we've got to think about where the repressor protein would be to turn this operon off. So remember, if the repressor protein is bound to the operator, then it's going to be in the way. So that means that now our RNA polymerase will not be able to bind to the promoter, because our repressor protein is in the way and no transcription is going to occur, and our operon will be turned off. Okay, part C of the question will be, well, how would we turn this operon on under negative transcriptional control? Well, we want to turn the operon on when our substrate is present. Okay, so maybe lactose is present. Okay, that's our substrate. So we'd want to turn this operon on. So we've got to get our repressor protein off the operator. We got to get that out of the way. So remember that when things bind to proteins, they change shape. So that's what we're going to do. We're going to have our substrate, maybe it's lactose in this case, bind to the repressor protein, and that'll change the shape of the repressor protein, and then it'll fall off the operator, and that'll get it out of the way. So let's go ahead and draw that. Here's our substrate. It's bound to the repressor protein, and when it does that, it's going to change the shape of our repressor protein, and that's going to cause the repressor protein to fall off the operator, and now our repressor protein is out of the way. Okay, so now our RNA polymerase is able to bind to the promoter and then it can just travel down the DNA and then go ahead and do transcription. I'll go ahead and transcribe those genes. And then those genes, the mRNA will get translated, and then we'll make those proteins and our operon is turned on. Okay, so that is negative transcriptional control of an inducible operon. So let's take a look at our second scenario that I could put on the exam. So we've got negative transcriptional control of a repressible operon. So remember, with negative transcriptional control, we're going to be using a repressor protein to turn our operon on and off. And in part A of the question, I would just ask the definition of a repressible operon. And so a repressible operon, remember, is turned on unless there's too much end product. So for example, we talked about like the trip operon, so the tryptophan operon. So this one would always be turned on unless you've got too much of your end product tryptophan around, and then you'd want to turn it off. Okay, so the second part of the question would be, well, how would this repressible operon be turned on if it's under negative transcriptional control? So this would be part B of our question. So if we're using a repressor protein, we want to think about where the repressor protein would be if this operon is turned on. So remember that the repressor protein, its binding spot on the DNA is always the operator. And remember, when it's bound to the operator, it turns it off. So it's in the way, and RNA polymerase can't bind the promoter, we can't do transcription. But we want this turned on, so that means our repressor protein is not bound to the operator, so it's out of the way. Okay, so that means that our RNA polymerase can bind to the promoter and then just move down the DNA and then go ahead and transcribe these genes and make the messenger RNA, and then those messenger RNA can be translated, and then we can make those proteins and our operon is turned on. Okay, but what if, in our third part of the question, what if we end up with too much of our end product? So that would be the third part of the question. If we have too much end product, we want to turn our operon off. So how do we turn this operon off if we're under negative transcriptional control? So we want to use our repressor protein to turn this off. So we needed to get it to bind to the operator. So in order to do that, we need to get it to change shape to bind to the operator. And remember, when something binds to the protein, it oftentimes will change shape. And so if we end up with too much end product, maybe like tryptophan, that can bind to our repressor protein, and that'll make it change shape, and then it can bind to the operator. So let's draw that. So here's our repressor protein. And then if we have our end product, maybe this end product is tryptophan or something. So when we get too much end product, it binds to the repressor protein. That's going to change its shape. And now the repressor protein can bind to our operator. And now that the repressor protein is on the operator, it's now in the way. And that's going to prevent the RNA polymerase from binding to the promoter. And so it's not able to do transcription. And so that's going to turn off our operon, and we will not make those proteins that the operon is coding for. Okay, so that is negative transcriptional control of a repressible operon, how we're going to turn the operon on and off using the repressor protein. Okay, and then this is just a picture of what we drew in those two scenarios. So this one up here on top is just showing negative transcriptional control of an inducible operon. And so over here on the left, it's turned off. So you can see the repressor protein is bound to the operator. And then they haven't drawn RNA polymerase in here, but if we drew the RNA polymerase, it would not be bound to our promoter. And so there's no transcription here. So that would be off. And then to turn it on, because remember, inducible operons are going to be turned off unless the substrate's present. So our substrate is going to bind to the repressor protein. That's going to change the repressor protein's shape. And then it falls off the operator. And then that's going to allow our RNA polymerase to bind to our promoter here. And then it's already started transcribing. And then here's our messenger RNA. And here it is turned on. Okay, and then on the bottom, we've got negative transcriptional control of a repressible operon. So remember, these are always going to be turned on unless you've got too much end product. So over here on the left, it's turned on. So the repressor protein is not bound to the operator. RNA polymerase is bound to the promoter, and it's already started transcribing. And here's your messenger RNA that you're making here. So it's turned on. And then if we get too much end product, we're going to turn it off. And so the end product binds to the repressor protein. That's going to change the repressor protein shape. Repressor protein binds to the operator. And then RNA polymerase cannot bind to the promoter here in green. And so there will be no transcription, and that will turn the repressible operant off.